and gentlemen, our class recording for today has started. So, yesterday, we started talking about the idea of orbital filling, and we introduced the idea of orbital diagrams. And we said that over the previous 4 days, right, we had pieced together this picture, right? All these different orbitals, all these different places that electrons are likely to be. But we find out that even though these are all likely places for electron, some are more likely than others, right? First, that's going to sound bad, but first, what's the one real key factor that determines how likely this likely place is to be filled? What determines which orbitals get filled first and which orbitals get filled next? How close it is to the nucleus, Ronnie, which relates to what? Is that what you were going to say? That determines how many electrons we have to deal with. How close it is to the nucleus, which relates to the energy of that orbital, right? And we always fill things from lowest energy to highest energy. Yesterday, we gave that a name. What do we call the idea that electrons fill from lowest energy to highest energy? Anybody remember? The Aufbau principle, right? So the Aufbau principle tells us that orbitals are filled from lowest energy to highest energy. And that idea is represented with this chart, right? As long as we read it, how? Bottom to the top, right? Okay. Side points. Do we have to memorize this chart? No. It will be on your test, right? Somebody last class asked, so I thought I would clarify here. Okay? All right. Good there. Yes. All right. What I would like you guys... Good. Good question. Jules asked if we are going to be allowed to use your periodic table on the test. You will get a periodic table, but not your periodic table, all right? See this right here, this green one that's nice and laminated, right? You will get this on the test, okay? It has the name of elements, it has their atomic number, it has their symbol, and it has their atomic weight, which we didn't do this section. That's the information that's on here. So this is, whenever you need a periodic table for the test, you'll get this one, all right? Yes, Jafar. Let's hold on 1 second. All right. Hold on 1 second. All right. Yesterday, I believe we left off with oxygen. Oh, did we leave off of carbon? We did carbon. Okay. So here's what I would like you guys to do for me. Okay. It is not on your sheet. Okay, so maybe you can do it in the margin on the side or down at the bottom of the second page. There's some space. Either by yourself or with the person next to you, draw for me the orbital diagram for oxygen. Okay, so either talk to the person next to you or do it by yourself. Draw for me an orbital diagram for oxygen. Were you paying attention yesterday? First thing you have to do is what? What's the first thing you have to do? Okay, so start with that. Oxygen. No, I haven't done the rest. So first thing we have to do in drawing an orbital diagram is determine how many electrons we have to place, right? For oxygen, that number of electrons is 8 because that is oxygen's atomic number, all right? Yep. That's what I want to see if you guys remember. Yeah, I did. No. All right, so let's discuss Okay? So first, Aufbau principle states that we fill orbitals from lowest to highest. So we go to our chart and we find out that the lowest energy orbital is always which one? 1s. So we draw our line that represents 1s. How many electrons can each orbital hold? 2. So this orbital can hold 2 electrons, right? There we go. Okay? You tell me, does it matter if it's up and down?
No. Yes.
Okay? If there's 2 electrons, it does, right? How do we have to write our 2 electrons? 1 up, 1 down, right? We learned about that in the previous section. What did we call that? The idea that 1 electron has to be up and 1 electron has to be down. The spin, there's a rule that tells us about the spin. It's on your outline if you want to look it up. So. The Pauli exclusion principle. So, 1 arrow up, 1 arrow down. Is that orbital full? Now it is, right? So we go back to our chart. What's the next lowest energy orbital that we come across? 2s, right? So here's a line that represents our 2s orbital. How many electrons can it hold? 2. Like that. All right? So we got 4 electrons down. We got 4 more to go. We go back to our chart. And we find that the next level orbital that we come across is 2p. But how many p orbitals are there?
3.
There are 3. When we are writing orbital diagrams, we write all 3 of them. Why do we have to write all 3 of them? We talked about this yesterday. Because there's 3 of them, but also, where are they on the chart? They're x, y, and z in the diagram on your chart of orbital energies.
Well, the second column.
They're all at the same level, right? Meaning, should probably pull that up for recording, right? They're all at the same level. Meaning what about their energy? They're the same energy, right? Is there any advantage to an electron being in this p orbital versus this p orbital? Neither one of the 3, none of the 3 has less energy than the other one. They're all the same. That being said, that led us to the last idea or the last rule that governs where electrons go. And we got to it right at the end of class yesterday. Do we remember what we call it? Hund's rule, right? So Hund's rule basically says what about our electrons? Devin, go ahead. Electrons will not pair up within orbitals of the same sublevel until all sublevel or all orbitals have at least 1 electron, right? That's what it says on your sheet. What does that mean in real life about where we put these electrons? What do we have to do with them as much as we can? Not fill them up. Spread them out as evenly as we can, right? So, now, I won't be able to tell whether you guys write it this way or not, okay? But, where does electron number 5 going to go? 2p. There's 3 of them up there. Which one? Technically, it doesn't matter. Usually we put it there, but technically it doesn't matter because all 3 of them are exactly the same. All right? Where does electron number 6 have to go? Actually, it doesn't matter. As long as it's not where?
On the same one.
As long as it's not this one, it really doesn't matter. That's Hund's rule. So that's electron 6. Okay? Then electron 7 has to go where? In that last one, because Hund's rule says we're going to try and spread out as much as we can. So now each one of these orbitals has 1 electron. But are they full? No. So now where does the 8th electron go?
First two, three. Doesn't matter.
Technically, it doesn't matter. It can go in any one it can go in any one of those three. Usually we draw it in the first one, but it really doesn't matter. Okay? This is the orbital diagram for oxygen because we have satisfied Hund's rule and spread them out as much as possible. Okay? Good there?
Yeah.
Okay. I'm going to skip. I think the next one on your outline is neon. Is that correct?
Yeah.
Okay. Next one I'm going to give you is sodium. So either on your own or with the person next to you, draw me the orbital diagram for sodium. Yes. I would. All right. So, correct answer for sodium is up on the board. Any questions? Good there? Okay. All we do, right, once we hit 10 electrons, all of the 2p level orbitals are full, right? They all have 2. So we go back to our chart. Off-bow principle says lowest to highest. We hit 2p, all full. We hit 3s next. Okay? Good there? All right. Next one I want you to do is phosphorus. All right. A possible correct answer is up on the board, right? How could we change this? Good question, Ronnie. All right, so Ronnie asks, would it be wrong if we did this? Is that what you're asking? So, is that wrong?
Yes.
Yes, that's wrong, okay? Because here we're not satisfying Hund's rule, right? We haven't spread out our electrons as much as possible. So this one has to be over here, right? Now, what could I change if I really wanted to? These three arrows right here don't necessarily all have to be going up, right? They could go up, they could go down. As long as we're not pairing up, it really doesn't matter. Okay? All right, good there? All right. I think the next one that's on your outline is argon. Is that correct?
Yeah.
I want you to skip argon, and I want you to go straight to potassium. All right? Orbital diagram for potassium. Go. Do potassium. What? Are there going to be questions like this on the test? Absolutely. It's like 3 points. Then, right? Where should we check? That's where that's why I gave you this one. So. All right, so let's discuss potassium. First, this is not the right answer up on the board. Okay. All right. First, it only sorry, this is. And then, yeah, I just 2p counts for all three of those. Just I'm getting lazy and I don't want to write them all anymore. So, okay. All right. Now, but the more important thing here, okay? This is 18 electrons. Okay? We need to place 19. There's 18 up on the board right now, so we're not done yet. Now, Ronnie, the question you asked me, right? On our big elaborate drawing of orbitals, right? After we drew the 3p electrons, right? So there's 3s, or there's 3s, there's 3p, right? The next one I drew for you was what? I drew what shape first? Butterfly was next, right? A blue butterfly was the next thing that I drew. Okay? And we called that what kind of orbital? That's a d orbital, specifically a 3d orbital, because it's in the third energy level, right? And then I added the green sphere, okay? But, so that would be what? Level 4, what kind of orbital? S orbital, because it's spherical, okay? Now, that's how I drew this drawing, for a reason. But, when we talk about what orbitals get filled, we have to go back to our off-bow principle. And our off-bow principle says lowest energy to highest energy. So we go to this chart. 1s, 2s, 2p, 3s, 3p. The next one that we come across is 4s. Okay? Hey. Even though technically the fourth principal energy level is higher than the third principal energy level, what we start finding out is as we get to higher and higher levels, there is more space, right? We said that the 1s orbital, the reason there's only a 1s orbital is because they're so close to the nucleus, those electrons don't have room to spread out. But as we get higher and higher up this chart, there's more room, there's more areas where we can get close to the nucleus, but still stay away from all the other electrons. Okay? This chart that represents the Aufbau principle is made by measurements. These are actually recorded values of these orbitals. In reality, even though the 4s orbital is a sphere and it's in the 4th level, it's actually less energy than the 3d orbitals, right? So when we're writing our orbital diagram for potassium, the next orbital that we come across after 3p is 4s. Even though we haven't completely filled all of the 3s yet, 4s is still the next lowest energy. Right? And then 1 electron goes there. Okay? Rodney, go ahead. Is that going to be on the test? There's probably a good chance you're going to see something like this on the test. Really, this is basically, can you read the chart from bottom to top, right? No. You don't have to describe why it happens. You just need to be able to read the chart. Okay? How many electrons do you have to place for potassium? 19. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19.
Yeah, but no. Says that, I thought those orbitals go first.
Right. This one's not filled yet. You only can fill the first thing we do when writing an orbital diagram is to do what? This. You have to know how many electrons you have to place.
Yeah, but
Just because they go low to high, that doesn't mean they always get filled though, right? That's why we went from 3p to 4s instead of the 3d. But you were talking to Jafar the whole time I was explaining that, so you might not have heard it. So. Yes, Jafar.
Oh, you erased that again. Okay. Spot to the left. Oh, got it. So, you know how there's 3D?
Yep.
Can you put like 2 on 4S and put like take one up from 3P off?
No.
Or do you have to fill everything?
Can you?
forward?
You tell me. These orbitals have lower energy than this orbital, so these are going to completely fill before we go here, right? Yes, so that was a valid question. Yeah, even though we may arrange these differently and still have 19 electrons, we had to fill the lowest ones first. Okay, Stephen, go ahead.
So let's say we have,
Hang on a second while we answer this question. For those of you that are okay with the last one, do manganese next. Okay, go. Make sure that you do manganese and not magnesium. Those are 2 different things. All right. Make sure you do manganese and not magnesium.
Oh, you count the thing.
I'm going to put it up on the board in a second.
like, you're confusing me. He's saying 4 feet goes first. Okay.
No. Talking about, do not listen.
All right, so as far as manganese goes, looking at our off-bow principle chart, we've seen 1s, 2s, 2p, 3s, 3p, and then we've seen that 4s is actually lower on the chart than 3d is. Okay? So we fill up the 4s, and that gets us to 20 electrons. But manganese has 25 electrons. So we continue reading the chart. The next set of orbitals that we come across is what? 3D. How many d orbitals are there? There are 5 d orbitals. 1, you could just remember that. Or 2, if you look at the chart, how many lines are there next to 3d? 5. So we draw in the 3d orbitals, 5 spaces. But we have to line them up this way. Why? Because of what? Hund's rule, right? That we have to try and distribute electrons as evenly as possible before they start pairing up. Okay? Good there. Okay. This picture is a simplification of, this orbital diagram is a simplification of this picture, right? Especially, right, when we start adding all these in, okay? We could draw little dots on this picture to represent where electrons are, and it would kind of accomplish the same thing. But it's pretty complex and kind of confusing if we put a bunch of dots on it. Here, this is a little simpler, right? It's more streamlined. It doesn't have as much detail, right? We don't know that a 4s orbital is spherical from looking at this orbital diagram. But those are things that we're supposed to know, right? If you know about atomic structure, you know that s orbitals are all spherical, okay? So this is less detailed than this, right? But it still gets the job done. It still tells us where electrons are. Now, even with this one on manganese, this is getting pretty complex, right? It's getting pretty long to do all this. So we have another way that simplifies it down even more. And we refer to that simpler way as an electron configuration. This is page 4 of your outline. Okay? Electron configurations are a shorthand way of representing the location of electrons around the nucleus. That's what an orbital diagram does as well. But here, not as much detail as an orbital diagram, but a convenient way of showing patterns and simplifying what we know a little bit more about it. Okay? Basically, and this is, I hope I'm not too off base with this comparison. Okay? Somebody in the previous class asked, well, why do we have to keep doing this? Why are we keep making it simpler and simpler? Well, it's just a shorthand way of representing stuff. Okay? For instance, in a text message, right, you use either emojis or you use letter representations instead of typing out full words, right? If you write LOL, people know what you're talking about, right? I know it's out of date. Nobody writes that anymore, right? But some people do, but anyway. But that's kind of what this electron configuration is doing for us. It's representing where all those electrons are without having to draw that big picture each time. Okay? Good there? But because you know English and you know what LOL means, right? You get meaning out of it even though we haven't shown you everything. Okay? So, let's go back. I'm going to do my electron configurations right here so you can see the comparisons. You have a space on the back of your outline. If you want to choose to do them there, or if you want to choose to do them where you drew your orbital diagrams, I'll leave that up to you. Okay? All right. Here's our orbital diagram for hydrogen, right? We only had to place one electron. We put it in the 1s orbital because that's the lowest energy orbital. I'm going to write my electron configurations in purple so we can tell them apart from the other two, or from the other ones, okay? when we are writing electron configurations, here's what we do. We start off with writing the orbital that electrons appear in. So this is going to be 1s. And then we use a superscript to represent an exponent, okay, to represent how many electrons are in that orbital. How many electrons are in this orbital? Just one. So we'll use that to represent the one electron that's in the 1s orbital. This is the electron configuration. Okay? Here really hasn't saved us a whole lot of time. Okay? Hold on, let me do one more, then you can ask questions, right? Okay? So next, here's helium, right? 2 electrons. Pauli exclusion principle tells us one goes up, one goes down. When we write our electron configuration, here's what we do. We write the orbital, 1s. And then we use the exponent to represent how many electrons are in that orbital. So how many electrons are in that orbital? 2. This is the electron configuration for helium. What doesn't it tell us? Well, what doesn't it show us? One's up, one's down. It doesn't show us that, right? It doesn't have as much detail as an orbital diagram. But because you know about atomic structure, you know that if we have 2 electrons in the same orbital, one of them has to be plus 1/2 and one of them has to be minus 1/2. Or one of them has to go up and one of them has to go down. Good there? Okay? Not as detailed, but still represents the structure. Here's lithium, right? Here's our orbital diagram for lithium. First orbital that we come across was 1s. How many electrons are in that orbital? 2. Then we had to go up to which orbital next? 2s. So we write that, and then we use 1 electron. Okay? So, by the way, sorry. When we are talking about, when we are saying an electron configuration, we say this as 1s2, 2s1. It's not 1s squared, okay? It's 1s2. We just say the number. Just go ahead.
The ones with more than one orbital, you put it all.
That's where I'm going next. That's where I'm going next. That's next. So, the short answer is yes. Okay. All right. So, let's skip up here to carbon. Okay? Carbon, electron configuration. 1s2, right? 2s2. Okay? Now, here's where the shorthand starts taking effect. When we have a sublevel that has more than one orbital, right? There are 3 p orbitals. Okay? When we wrote our orbital diagrams, I told you to write all 3 of them, even if some of them don't have electrons in them. Shorthand, we don't do that. So we just write 2p. And then we write the total number of electrons in the 2p orbitals, right? So how many here, right? This is 2. But Lauren, we can have how many total? You can have up to 6 total. Okay? Now, what doesn't this electron configuration show you? Doesn't show you Hund's rule, right? It doesn't show you that these 2 electrons actually aren't in the same orbital, right? But that's something that you need to know to interpret an electron configuration. It's a shorthand way of representing where the electrons are, right? So, here's oxygen, right? Remember, I didn't have you, oxygen isn't on your original list. I told you to add it, okay? But if we're going to add it, right, we start off 1s2, 2s2, and then 2p4, because there's 4 total electrons in the 2p level. Okay? Jason, does that help? Feels good. I will ask you on the test, the question was on the test, will I ask you to write it one way or the other, or can you pick one? There will be specific questions that say write the orbital diagram, and there will be specific questions that say write the electron configuration. So you're going to have to know the difference between the two of them. The orbital diagram is the boxes and the arrows. The electron configuration is this. Okay? Good there? How we write electron configurations, the order that the orbitals are filled doesn't change though. So for sodium, 1s2, 2s2. Lauren, how many electrons in those p orbitals? There's 6 here now, right? And then, after those p orbitals are filled, we go where? 3s. How many electrons in that 3s orbital? Just 1. Right? Same thing is true about potassium, right? I'm skipping some because I want to get through a certain point because we're getting close to the end of the period, right? 1s2, 2s2, 2p6, 3s2, 3p6, but the order that the orbitals get filled doesn't change just because we've gone to a shorthand notation. The next orbital to get filled is still 4s, 4s1. Okay? Sure? Okay. And then finally, for manganese, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So the question was, don't you need to see the diagram to know where they go? The answer to that is, this is a shorthand way of representing this. Well, that depends. Is it harder to write the configuration without the orbital diagram? If you don't know the structure, yeah, right? But what I'm saying is that when we start looking at, like, not so much our book, but like future books, like higher level chemistry books and stuff like that, they're not going to write orbital diagrams for every time they want to talk about where electrons are, because this is too much to write for everyone. This is manganese and it only has 25 electrons, right? If we had to write an orbital diagram for uranium that has 92 electrons, right, it's going to be 3 boards worth of stuff. You know what I'm saying? But this is a shorthand way of representing that. It's not as detailed as an orbital diagram. But if you know Aufbau principle, and you know Pauli exclusion principle, and you know Hund's rule, you could take this purple and turn it into an orbital diagram. Does that make sense? That's what it's for. Okay? All right. One last thing before you take off. In my hand up here, I have a sheet of practice stuff. All right? If you go to the calendar on tonight that says homework, orbital diagrams, and electron configurations, when you pull it up, there is an attachment there. Guess what you'll find? Answers. All right? So I'll give these to you. Tomorrow we review for the test. Test on Monday.